Hi there, it's Lester Martin with Hortonworks University. We're going to continue on with this next module called Apache Spark as part of the larger Hadoop Essentials offering. So the objectives for this Spark module are much like the last few we've done, just making sure we have a good introduction of the technology. Spark, we'll definitely walk through the concept called the RDD, what that's all about. Talk about the additional frameworks that layer on top of Spark Core. All people like to think Spark means in-memory processing, so we'll definitely talk about that space, and then some of the other additional things that make Spark a very fast-performing environment. And then we'll finish up with running through those additional frameworks that we alluded to at the beginning, and as well as a demonstration using Spark. So, Spark, as that first bullet says, in-memory processing, in-memory data sets. That's what most folks are thinking about when they hear Spark. Obviously, it's part of the Hortonworks distribution, so it's Apache open source software. The languages that are supported with Spark are Scala and Python, probably the most to date, the most mature, Java, and then R as well. And what's slightly different here is that unlike, say, Pig, where we have a programming language called Pig Latin, here we have programming languages such as Scala, Python, Java, etc. And they have libraries that are Spark that are being utilized. So you really are building a normal application that has extension points into Spark. And we'll talk about right now, I guess, the RDD. And RDD stands for Resilient Distributed Data, or Resilient Distributed Data Set. And much of that really means is much like HDFS, how we partition files. Spark likes to partition, distribute data sets, especially large data sets, across many nodes. And it's resilient, meaning that it can handle the fact that being spread across many nodes may mean a node may fail for some reason, and just that part, or just those parts that are lost, can be rebuilt and recreated. And then, data set's a data set. So an RDD is the basic operating model for Spark. Now, we're not going to spend enough time in this introduction session programming against RDD, etc. We'll see a little bit of that in the demo, but I want to make sure you understand that's the cornerstone concept used in Spark. The sweet spot for Spark is probably that second line there: iterative in-memory computations and interactive data mining. And we'll talk about that when we get into this, the caching and in-memory conversation, how that could be much better than maybe traditional technologies that we've used in Hadoop to date. There we go, I mentioned some languages. And probably what's as you think about those white bullets across the top right up here, in addition to Spark Core, machine learning and streaming on a SQL engine of sorts, what we're really producing in Spark, and I think it is the most compelling argument to date to me for Spark, even more than performance, is we're having the opportunity to write in a common language, a language that you choose, that you have some choices that can span data processing, transformations, analysis, lightweight analysis, deep, rich, interactive, iterative machine learning type analysis as well. And I think if I didn't say stream processing as well, as opposed to what we have prior to Spark, where each one of those is a little different technology with a little different set of tools. And I think that's the biggest promise that I like to imagine from Spark. So we talked about this notion of an RDD earlier. As a promise, we're not going to go into a code level description of that, but I want to kind of give you a visual to see if it could make some sense. So across the center, what we're trying to emulate here is that trying to visualize the fact that we have a bunch of cluster nodes in our Hadoop cluster, and we have these two large data sets, data set 1, data set 2, and they happen to be broken down into 4 and 3 partitions. And just as a side note, when we read information into an RDD with Spark from a data set that exists on HDFS, the default behavior is that we'll have the same number of partitions for the RDD that we had from the partitions, the number of blocks that were made up that file in HDFS. We'll talk about a little later how you can change that partitioning bigger and make it smaller or make it larger as appropriate. But just want to make that point. And all this picture is trying to show is that if your cluster was running and within the cluster your Spark application has reserved these containers. We'll talk about containers as well when we get into Yarn, but they reserve some resources and we're running. They have these application spaces that this RDD may in fact be, and it most likely will be, very spread across the various cluster nodes you have. And here's a quick bullet, just some high-level things about some of the key focuses of Spark. Definitely we want to, we're talking a lot about Hadoop, and we want to imagine, Spark could exist without Hadoop. I think Spark with Hadoop is an extremely compelling argument. And since we have information already in Hadoop, not just flat files or Hive, like you see that first bullet, we have things in NoSQL System HBase, so we're going to be able to get that information quickly. We definitely want to interact with the data that Hive itself supports. And even those underlying files, those high-performance files like ORC files that Hive likes to front, Spark has its own processing model against those files, and in fact is very, very efficient. So we want to leverage the data that exists in HTTP. Like all things Hadoop, we want to encourage, enable, improve multi-tenancy. And probably, multi-tenancy, the things that we're talking about right now are around invoking things from a variety of locations, but probably security is probably the biggest one to implement in that space. And then lastly, I suggested just a moment ago that Spark could run differently than in Hadoop. We want to make sure that Spark runs the very best in Hadoop, and the very best of Hadoop is Yarn itself. Spark likes to go out and ask for a lot of resources, and has historically got some negative connotations for being able for reserving and maintaining and holding on to resources, regardless if they are being used at all, or being used heavily or not. So there's quite a bit of work in the Spark community, and especially how Spark interacts with Yarn, to make sure that we can scale down and scale up appropriately when those resources aren't being acquired, but also take care of the benefit of having those resources available. So we'll see a lot of continued changes in that space. And much like the other tools, Pig specifically is a good example that we have of this notion of an interactive shell. The Spark shell you hear a lot about. There's a Spark shell primarily for Python and Scala, two different shells for that. And we can build, since these are programming languages, we can build true applications and schedule those applications, invoke them at different times, and for doing our normal kind of data engineering functions. So you kind of see it working down that path, exploring, or even trying to build a productionalized work stream. You might work in the shell to kind of iron something out and get a feeling for something, and then if that's something that you're going to productionalize, often you'll see that code then find its way into an application proper. So in-memory caching, in-memory persistence is the thing that Spark has got a lot of press about, but I think there's a few other items that are worthy of consideration and discussion, so we'll jump on into that. So we'll focus on the fact that, and we're doing a little compare and contrast with Java MapReduce, but as the visuals show there, if we have a model, I think we said the sweet spot was we're iterative mining. We're constantly we're looking at a data set, we're making some interpretations, and then we're going to remake some interpretations of that data, slightly mudge it, evolve it, change it. In that world, that machine learning style of processing world, HDFS as the output medium for each one of those iterations has some benefits, definitely from restarts and those kinds of things, but has some performance constraints, especially if we're going past the 5 or 10 or 20 or 100 or hundreds or thousands of iterations that if we could maintain that information in memory, we would see a significant lift. So Hadoop itself came from a long path to make sure we had this data locality where the processing, the data that a process needs was on that same machine, etc. And that's still very solid, very sound, works for many, many use cases and workloads. But this kind of iterative workload, we really have to go that next step and really focus on in-memory data sets. Now, contrary to probably popular belief, everything that you read, every RDD, every data set that's loaded into Spark is not actually cached. That's not actually persisted into this in-memory concept. We have to explicitly, at the RDD level, persist that information. And that's good. We want to make sure we're doing intelligent things. We want to make sure that we're not reading something, producing something else, producing that into something completely different. And a typical transformation process probably wouldn't benefit overly heavily from caching every single step of the 10-step pipeline by the fact that we're not going to continue to go back and make changes or read that information again. In fact, it seems like it would be contrary to the performance gains. But definitely a data set that we want to evolve and change and keep growing or morph and roll upon itself. And just like I mentioned in HDFS, maybe as we're doing iterations, we may create this concept like a checkpoint every 5th or every 50th or every 500th iteration. If we snapshot and persist that information, we have an opportunity for the framework, if needed, due to failures, etc., to roll back to a certain point and progress. So I was letting you kind of read the screen there. There are a variety of options, and they're primarily a mixture of RAM and disk, kind of where this information should be persisted, how it should be backed, and then you kind of see in that third column there that we in fact could have things serialized. So the larger data that we have, but we want to get the benefit of it in memory, chances are we're looking at this notion of putting it in RAM, but I need to serialize it as well. We're still going to get lift over a serialized copy in RAM as opposed to something on disk that we have to physically read. So on this notion again of performance improvements, etc., some of these graphics and comments are right off the spark.apache.org site. And they're not intended to suggest that every single workload, every single use case, compare and contrast it with Spark and MapReduce, are going to see a 100x improvement. But there are definitely some use cases that makes a lot of sense. And so that's kind of the left. And the right is really just trying to give you a feel for level of complexity from writing something in Java MapReduce versus PySpark, versus Spark. That's the Python example above. So this is the old, if you look close enough, and I know you can't read the MapReduce, but this is the old word count example that we saw earlier in one of the earlier modules as well. So why is it so much faster? Well, for sure, we talked about using memory to cache information and not having to read that information, much less write it back to disk, pulling all that stuff out of memory. But just as much, Spark at runtime acquires a set of resources from the cluster, kind of that third bullet, a dedicated set of resources until that application is finished. So if you launch an interactive shell, what we're saying is whatever resources you go out and garner and wrap your arms around, and then you walk away, then those resources are consumed, and the cluster cannot take advantage of those at that time. That same concept exists for the duration of any Spark application. And by having those pre-built, pre-warmed up, readily available, and then coupling that with the fact that Spark has its own execution engine, has its own scheduler of tasks, we get a really awesome storm where we can run really, really fast. We have a very custom-built solution around not necessarily releasing resources, but garnishing. And basically, you could almost argue that this application itself is a mini cluster within a large yarn-based Hadoop cluster. So those are great ways to see improvements. And then, just like we saw with Tez, how it moved away from MapReduce from the constraints perspective, not necessarily from the philosophical perspective. You see that in Spark as well. Spark at heart still looks to MapReduce as a foundation, and still does mappers and reducers, or wide or narrow operations, they sometimes like to say, but they don't have the physical requirements that a Java MapReduce framework has around intermediate data between jobs, writing things to HDFS, and not allowing concepts like a reduce-only job. And this slide, just to kind of drill that point home, what I'm going to kind of walk through this builder is not try to explain that code across the top, but what's happening is we're showing a word count solution in Spark, and we'll see it with Python. And really what I want to make the point by kind of clicking through it and look at the lines of the code and looking at the figurative examples at the bottom, a couple different things. One, clearly we still are using MapReduce. Why? How's that easy to tell? Well, look at some of these method names. Maps, reduce. I mean, to a point now, a little more lower level than even Pig. Pig, we didn't talk in terms of map and reduce. Spark, many methods are still going to talk in this terms of map and reduce, especially as we operate on the rawest concept of RDD. And just like we're programming against that, in fact, you can kind of visualize, if you remember from the MapReduce conversation, we are seeing this notion of we can process information in parallel and parallel and parallel for these variety of things like splitting words together, flattening that splitted set of words together, even mapping. But there's a step, reduce, that has to happen. And to be honest, those parallel streams don't have all the values. They don't have all the words the. So we have to do this shuffle and sort concept to still get it to another piece of code that can ultimately reduce that. And then, in fact, we actually did maybe even do one more reduce, or reduce only, based on the values of these reduce. So we are still using MapReduce, and that's not a bad thing. That's a good thing. We're still basing our engine on those sound parallel processing fundamentals. We're ensuring, just like TES, that we don't have a lot of those physical requirements that could make MapReduce slow down. And then we're garnishing resources ahead of time so we can run very fast. And we're managing these transitions all within that preset of resources, as opposed to engines like TES, etc., that may be smaller in the process to go get these activities. And then lastly, I just want to kind of hit on it. While we drive in MapReduce, especially this notion that maybe a block size drives a map, and we talked about that when we showed the RDD, we can programmatically inside of Spark repartition, reparallelize how wide we are when we do these wide operations. If we feel like, and we tested, we found out that this step from here to here would be better suited to go up to 10 partitions, and then maybe this step is better suited to come back down to 2. Not suggesting that's the answer, but if that's what we validated through an assumption, we made an assumption, hypothesis, and then validated that hypothesis with some testing, we have that level of fine-grained controls to make those kinds of operations. So as we look past the basis of Spark, Spark core, and again, we'll do a demonstration at the end where we'll see some of this code in action, a simple example. There definitely is more to Spark than what we just talked about. And the good news is, as we add on additional things like SQL and streaming and the machine learning libraries, they're really just additive concepts to everything we just did. And all the programming, all the hard lessons you've learned are immediately applicable as we transition into these additional frameworks on top of core. So what are some of those? Well, definitely Spark SQL is the one that gets a lot of attention, etc. And in some ways, Spark SQL, it can be viewed as a competition with Hive. And what I mean by that is, we said Hive could potentially someday have an execution engine itself of Spark, and how that was not Spark SQL. And that model just suggested you would come to Hive. You would make a ODBC, JDBC connection to Hive, and then Hive might use Spark to get work done. In this, we're going to have an equally comparable listener out there that you can make a ODBC JDBC connection to, and then issue a query. And now the good news is this engine itself here can definitely leverage all the data that Hive knows about. It can interact with the metastore, etc. But it can look at any other data that's out there on HDFS and potentially other sources as well, and represent them as a classic table, result set, etc., with fine-grained details about column names, data types, nullable, and that kind of information. And as the last bullet kind of suggests there, while we can use SQL queries to do all the activities through Spark SQL, there is a rich data frames API. So the data frame is the concept. It can be visualized as a wrapper on top of an RDD to give it these additional characteristics that look like what you imagine when you run a query, per se. So a result set kind of concept was what I would equate to the data frame, and that data frame will leverage all those resilient distributed data set foundations. It just encapsulates, it isn't an RDD at its core, but it gives you a richer set of APIs and information to interrogate against that. And again, you can use that same data set even as a table. You can create an RDD, or read an RDD, spin it as a data frame, and then use that in a SQL statement with some other table that may exist in Hive. So again, Spark SQL can leverage Hive. It does not go to Hive and ask Hive to run a query. It interacts with Hive from the perspective of the metastore to find out where its underlying data, things like Avro and Orc and tab and comma separated values, those kinds of things, where they exist. But Spark SQL has its own execution approach. It physically reads those files. It doesn't go to Hive and run a query. Another one of those features that sits above Spark Core is Spark Streaming. And out of the gate, you could probably compare and contrast Spark Streaming with Storm, which we saw earlier in an earlier demo. And it is that real-time event processing kind of model. And what's a little different than Storm proper, at least, is that Storm worked on a tuple or a row at an event, a single event at a time, and flowed that data through the workflow. Spark Streaming leverages a concept called micro batches. So you configure, for example, an amount of time that you want to wait. Let's just have fun and call it a second. And then you're asking Spark Streaming to collect all the information that it's listening to for that period of time and then bulk it together. So that could be a record, it could be 10,000 records or 500,000 records, whatever it is, and create basically what looks like an RDD of those information. It's called a D stream. It's a little more detailed than that under the covers, but programmatically it looks and feels and tastes like an RDD. So what's really different here? Well, if this pink environment here, all this, if you take this yellow bar called the receiver out, what we really have is a running application. If you build an application that can read a file and load it into an RDD and then do some processing on it and make an answer, then you've built 90% of a Spark Streaming application, because what you're going to do is configure up a receiver to some kind of data stream, a message queue, a socket, a file, something to pull that in, and then configure those micro batches, and then that function that you created in Spark to chew on and process and work on an RDD is almost perfectly equipped to then take that micro batch at a time. And again, just like Storm, you're building a model that runs, not that you start, process a few things and turn it off, you just run forever. You constantly get these micro batches and consume and run on those. So very good concept. And again, if we didn't make the point, what's nice here is maybe in the past we wrote some transformations in Pig, and we wrote maybe a little more transformation or some analysis in Hive, purely as SQL. And then we realized we're going to do some front-end work with Storm to get some real-time events. So we wrote a little Java for Storm, a little Pig Latin for Pig, definitely SQL for Hive. And here's an opportunity, if we were starting from scratch or dramatically revisiting that architecture, to attack that problem with the same base framework, same base programming language, and reuse all those functions and points all the way throughout. And so as a software developer, this is my point about even if Spark wasn't faster than everything else that we have, that would be a very compelling argument for me to take a really hard look at Spark. And lastly, the big of the ones that we'll focus on here, the last large one is the machine learning library. This is your data science toolkit. These are those kinds of things, and we talked about how maybe DataFoo was kind of that data analysis toolkit of choice. Definitely ML Lab, that's bundled as part of the Spark project, is that place for the detailed algorithms that you see listed there and more. And again, this is that data scientist playground. And again, you're building it with Python, Scala, Java, R, whatever tool is most appropriate, or like many data scientists, whichever tools you want to take advantage of. So I did want to take a moment and just make it crystal clear. Hortonworks is very committed to Spark. We talked about how we want to make sure that the very best place to run, since there are choices of running Spark, a limited set of choices to run Spark, we want to make darn sure that Yarn in Hadoop is the place that's going to give you the very best environment, performance, scalability, etc. As we transition into that second tier, we want to make sure, like all things we do at Hortonworks, that we wrap it with enterprise readiness, tools for administration, support configuration, monitoring, definitely governance, security. Those are the kinds of things that we're really thinking about from an enterprise perspective. And we're definitely engaged and very open into the Spark community. And the Spark community is probably one of the widest open communities in all of Apache, to be honest. Very, very much interest and involvement from many, many places. So that's very, very excellent to see. And I'll finish up this section with mentioning Apache Zeppelin. So Zeppelin is the environment I'm going to do my demonstration in a minute. It's a web-based, I like to use that term, notebook, a web-based application that we're going to build. And it's much like a web-based interactive shell, is the way I would express it for starters, that you could run a lot of technologies in there, not just Spark, but run Hive queries in there, but a variety of other things, Pig, theoretically. And we've integrated Zeppelin with Embari to be laid down for monitoring, all those kinds of things. And ultimately, we believe it is that, data science studio, that modern data science studio that folks will come do their exploration, discovery, lots of visualizations, etc. Again, that's what I'll focus on the demonstration. Here's a quick screenshot of what you might imagine. As you see in all of those little windows, there's about 4 snippets, maybe paragraphs, people call them different things, here, 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 and here, and they all have something going on with them that drives something else. So very positive user experience. All right, we'll take a quick knowledge check before we move on to summary and then demonstration. So wondering if anyone remembered what the RDD acronym stood for. Well, it's a resilient, distributed, and then obviously data set. Resilient, distributed data set. Data is going to be spread across all the cluster resources that the Spark application is utilizing. It's going to be resilient in such a way that if we lose one or more of those nodes that we're operating within, the framework can realize that and just recover just enough that it needs to keep on moving forward. And obviously it's a data set. The languages were supported by Spark, or I'll say it differently, the languages that Spark has the rich library for. It's Python and Scala, Java, and more recently R. And I guess I'd ask, what are some of the features that make Spark's secret sauce when it comes down to performance? And there are a variety of things. I mean, definitely most of these are just core to Spark. Spark holds on to resources for long periods of time, for the entire length of the application. That's huge because we don't have to go to the resource negotiator, ask for things, potentially get an answer, maybe get a no. We already have all that information, all those resources ready to go. definitely we have the opportunity, once we start loading data into RDDs, we have the opportunity to cache that information. Spark has its own scheduler, the scheduling of tasks, those mappers and reducers, for example, that we showed on the word count. He is spinning those up, deciding where to run them and everything. And then probably just as much as anything else, the kinds of concepts that things like TES also took advantage of. Have reduce-only jobs, don't have a need to write data to disk, much less HDFS, if not needed. I mean, those are very, very important. I guess lastly, I would mention, again, the fact that you have a lot of programmatic fine-grained control on scaling the amount of parallelization if you want to experiment and do some testing to find out what's the optimal environment at every single step along the way in their execution of a program. True-false question: RDDs are not persisted in memory by default. I think I've kind of beat that one home. They are not. You have to explicitly store them into memory, and you have to expect an environment can deal with what happens when there are too many things in memory, and least frequently used type eviction processes and all those kinds of things are going to come to bear. So you need to be intelligent about what you want to persist in memory, not just every single RDD that is created persisted. And one last one. I guess it's a two-part one. So Spark, which of those Spark extensions or add-ons that we talk about utilizes the D-streams? I probably didn't say D-stream that loud. It was on the slide. D-streams are part of Spark streaming. They are the thing that I referred to as a micro batch that acts like and tastes like an RDD that then you can process in Spark. And then data frames is definitely equated to, was introduced in Spark SQL, and data frames is a wrapper around an RDD to give rich schema, definitions, column names, column types, etc., as well as an opportunity to take other RDDs, wrap them as a data frame, apply the schema, and in fact leverage those new data frames as a table that you could then maybe put in a join with another table and actually interact with that with SQL. So there's the quick summary. I think we just talked about most of those things, the things that make Spark go quick and fast, RDDs, languages, and memory that you need to choose. And finishing up with, I guess at the very end there, MLlib and Apache Zeppelin being the foundation for this modern data science studio. So that takes us to our tutorial. Now this tutorial is going to be this, in essence, the same requirements that we did in the other one called risk analysis with PIG. We're going to solve the same problem around trucking data, around which drivers are the most riskiest, what kind of areas, etc. What kind of parts of the town are they driving around that seem to be causing them problems. And we'll do it all in the Apache Zeppelin notebook.